Well, now let's take a look at example number 2. This will be really our first full example of how to use this idea of a trig substitution. So I'm going to go ahead and notice here that I'm starting with a radical, kind of like one that we dealt with in the table up above. Now, I don't actually want to go back to that table to look at it. I'd like to try to reason through again how I'm going to attempt to simplify what I have here. Now, the reason I know that I'm going to be able to use a trig substitution here, or at least that I'm going to attempt it, is because I've already actually quickly in my mind thought through all of the other techniques, and I don't really see any of them fitting. Notice that you don't have any derivative rules which result in this from Calc 1. It's difficult to know how you might simplify what you have here using algebra. A U sub doesn't really seem like it's going to work, and integrating by parts would be really hard, and using trig identities doesn't make any sense because there's no trig involved. So let's actually start by thinking about how I would actually go ahead and replace x. Remember that I'm always going to need some number and then some trig function. Those are multiplied together. Now, when thinking about the number, I want to think that that number is going to go in place of x and get squared. And so I'd like that to match the 9. Therefore, I'm going to pick the number 3. 3 squared would match the 9 and allow me to eventually factor out. Now, this is where you have to be able to think a couple steps ahead. Once that 9 gets factored out, I'm going to have 9 times the quantity 1 minus a trig function squared. And so I'd like to think, what trig function could I square and subtract from 1 so that this looks like an identity? Well, there's actually a couple different options, but one option that jumps to mind for me is sine of theta. Let's see how all of this works out in this specific question. I'm going to go ahead here and quickly calculate my dx as well. Notice that's going to be 3 cosine of theta d theta. I also know that I'm going to need an angle restriction on theta, but I might not remember what I'm supposed to choose for that, so I'll come back to that in just a moment. So if I use this substitution, then I'll notice that the integral that I have will be able to be updated slightly. Notice, again, I'm going to have 9 minus 9 sine squared theta under the radical. In my denominator, I still have to take x and square it, so I'm still going to have a 9 sine squared theta. And in place of dx, notice I can't just write d theta. I actually have to replace dx with what it's equal to, which is 3 cosine theta d theta. So things here will look a little bit messier before they get neater. Now let's see. I can simplify down a bit more. One thing that I'll note is that the radical can be rewritten so it's 9 times 1 minus a sine squared under that radical, which is of course really convenient for us. I'll leave everything else as is. Under the radical, 1 minus a sine squared, I know that's a cosine squared, and so I can rewrite that as 9 cosine squared theta, all under my radical, 9 sine squared in the denominator, a 3 cosine on the outside with my d theta. Now I'm going to keep going. I'm going to see here, again, in the numerator, I'm going to end up with a 3 absolute value of the cosine, and then a 9 sine squared theta, and a 3 cosine theta d theta. It is so important, again, that you don't skip over that absolute value step here. I have to have absolute value bars. Now, I'd like to simplify this down a bit further, and a couple things jump to mind right away. Like, I can simplify 3 times 3 makes 9, and dividing that by 9, those are all going to cancel out. But what do I do with the absolute value bars? Remember, it's in exactly this step where I need my angle restriction. I need to have a range of angles where the cosine is always positive. And if I think back to my unit circle, the cosine would always be positive in quadrants 1 and 4. So that would be from negative pi over 2 to positive pi over 2. So now I can go ahead and rewrite this as a cosine of theta over a sine squared theta times a cosine theta d theta. Of course, you might see that I can simplify that down a bit more, right? That's really going to be a cosine squared over a sine squared, also known as a cotangent squared. Okay, so this is a lot of work already, and what it's allowed us to do is to take this integral over here that was complicated and turn it into this one, which we hope is going to be a bit simpler. Now, what in the world could I do with the integral of a cotangent squared? All right, let's go right back to the main list. Let's see, is that a derivative rule that you know from Calc 1? Not really. We had like secant squared or negative cosecant squared as derivative rules, but not cotangent. Can we do any algebra to make this look simpler? Not really. U substitution seems hard. Oh, wait. What if I used a trig identity? I know that the cotangent squared is the same thing as the cosecant squared of theta minus a 1. So now, can I integrate each of those pieces? Well, sure. Cosecant squared actually comes from a negative cotangent of theta. The antiderivative of 1 would just be theta, and don't forget at the back, plus c. And here's the disappointing part. We're not quite done yet. Can you tell why we're not done? Well, think about how a u sub would typically work. In a u substitution, you would perform your substitution, get your variable with u's, you'd go all the way down to the end, you'd get an antiderivative with u's in it, and then you would have to put things back in terms of x. Okay, well, maybe this isn't too difficult. I just need to know what is the cotangent of theta and what is theta. Well, here's where things can get a little bit confusing. Let me go ahead and at least write down that now we need to get things back in terms of x. So here's how I'm going to do that. I'm going to go ahead and go back to my original substitution, which was 3 times the sine of theta, and I'm going to notice a couple things. First off, I'm going to notice that that would imply that x divided by 3 is equal to the sine of theta, and here's where I have to be very careful. What would then the inverse of inverse sine of x over 3 actually equal? Now, it's very tempting to just say theta, but you have to remember something. Inverse trig functions can only tell you angles from certain ranges. So again, inverse sine can only tell angles, or can only, instead of saying tell, I'll say make. This can only make angles in the range negative pi over 2 to positive pi over 2. It cannot produce any angle outside of that range. So is theta an angle in that range or not in that range? Do I know? Well, this is where something very convenient occurs. Notice, where did we say theta was? In between negative pi over 2 and pi over 2. It is in that range, so I can say that the inverse sine can actually produce that angle. This is really important. That's why in the very first video of the section I said you may need to go back and review some things about inverse trig functions, specifically what angles they can output. So with this in mind, I now know how to replace this value of theta. Technically, I could replace this value of theta as well, but I think we could do something even nicer. I'm going to go ahead and from this step right here, I'm going to go ahead and pull some extra information. Now, I know that my angle theta is an angle in quadrant 1 or in quadrant 4, right? Because we said it was somewhere from negative pi over 2 to positive pi over 2. Let's suppose, for the sake of argument, it's in the first quadrant. So this is my angle theta. Well, if I was to go ahead and draw in a nice right triangle, if I know that the sine of theta is equal to x over 3, that would be my opposite side over my hypotenuse, I should be able to solve for this missing side using Pythagorean theorem, right? That side would be mystery value squared plus x squared equals 9. So that mystery side that I have right there should be equal to the square root of 9 minus x squared. So I'm going to go here and actually write in that value. This side's got to be 9 minus x squared under a radical. But if I know this triangle, can't I find what the cotangent of that angle is directly? So let's see. The cotangent of my angle minus theta plus c is the same as, let's see, cotangent should be adjacent over opposite. So my adjacent side is this. My opposite side is x. Theta we found was the same as the inverse sine of x over 3, and we still have a plus c. I have now a final answer. And I know a great way you could check your work. It's take the derivative, but this is actually a little ugly to take the derivative of. You could do it, and you could actually see that you do indeed get all the way back to where we started up here. Now that is a lot of information to tackle just one question, and so you can probably see that there's going to be a lot of practice required for this section. We'll take a look at another example of this in the next video.